My name is Suresh Srinivasan. I'm the coordinator of the Beginner Special Interest Group for the Minnesota Astronomical Society. Excited to introduce Ahmed Reda, who's a member of the MAS board. He actually just finished his master's degree. Is that an accurate statement, Ahmed?
Yes.
Just in the last day or week or so. So it's exciting for him. Anyway, Ahmed's on the MAS board as a member at large. He's also very active in at ELO, Eagle Lake Observatory, with the outreach programs that we have out there. He also coordinates all the guest speakers for the monthly events, the monthly MAS events in Roseville. So today he's going to talk about Islamic astronomy, and I'm very excited to hear it. So go ahead, Ahmed. It's all yours.
Thank you, Suresh. And thanks everybody for joining us today, especially on a snowy day. Pretty much this topic, when Suresh and we've talked about it, was something that we started talking about it seriously about 2 months ago, but we've been talking about it for a while because the influence of Islamic astronomy and how it was effectively a melting pot for a lot of cultures, preserving the past and evolving and laying the groundwork for modern astronomy is very crucial. And it's not a short period of history, it's about a millennia. And you have a lot of produced output during that millennia, and it was pretty challenging for me, actually. There was no shortage of material or things to talk about, but the question was what to pick and how to consolidate it in a high level to give people a very high level perspective, because in 90 minutes I can't do this any justice. Some of the astronomers here, I can talk about them for hours, what they've done and the methodologies they've done, and it's just mind-blowing. And some of the stuff I'll be sharing with you, just how accurate they were, even in contrast to some modern measurements, like the circumference of the Earth and the period of the full solar year, etc. It's just mind blowing, the methodology, the approach, the theory work that was done. And to start this off, I'm actually gonna start talking about the entire region. Where did this all start from? And it all started from the Arabian Peninsula. And the Arabian Peninsula is effectively, you can say, it's at the crossroads of human migration, between Africa, Asia, and into Europe. And pretty much you have, stone, hominid remains that go back to half 500,000 years. Those remains are found over there. So humans have been in that region for a long period of time. And there are Homo sapiens remains that go back about 180,000 years in that region. Now, that entire region was throughout its history dominated by Semitic people and Semitic languages, as it functioned in the crossroads between, whether north of it was the Fertile Crescent in Iraq and present-day Syria, and south of it, you have civilizations in Ethiopia and some of it in Yemen. And those are, in the early ages of human civilization. But then in antiquity later, it was in the crossroads between the Persians and the Romans. Yet, there were some interactions, but yet it was still isolated to some level. So pretty much, when you look at the Arabs, living in that region, that's the name that historians agreed upon, in the Arabian Peninsula, people who lived there, the different tribes, the different groups were all Arabs. When you have the northern Arabs and the southern ones ended up adopting a sedentary lifestyle. So the ones that were either, on the border with Syria, they settled down, they built, palaces, tombs, and they became part of the sedentary civilization. And some of those are, famous names like the Nabateans and the Palmyrans. And, you got the Canaanites are directly related to the Arabs. And those in present day, Syria, they pretty much built civilizations. Same thing in Yemen. At the same time, the region that's in between, the bulk of, the central part of the Arabian Peninsula, present day Saudi Arabia, those actually remain nomadic. And the interesting thing is what we know about them from pre-Islamic period is primarily oral traditions that were carried down from one generation to the next over hundreds of years. Eventually, it was recorded after Islam. Before Islam, there weren't a lot of people that knew how to read and write. Writing was not a common thing in society, and mostly it was an oral tradition. But pretty much those, those cultures and those groups had their own, astronomy to some level, which was primarily observational. And they also had a high level of astrology like other cultures, and that astrology even fed into their religions. And we'll be touching on that shortly here. So pretty much, across the Arabian Peninsula, the people over there, in the north and the south with the sedentary life, there was agriculture, there was, some level of tool manufacturing and trade and other stuff. But then the ones in the middle pretty much relied primarily on trade. And to them, they were effectively the connection between the trade routes going from the east to the west and the trade routes going from the north to the south towards, the civilizations in present-day Ethiopia / Abyssinia and into Africa. And they played a key role for that. If you go walk through the desert, you come to recognize how clear the sky is, how amazing it is, and how effectively the only features that you can recognize to go from point A to point B are the stars. And this is where astronomy became very important to them. It became the way they navigated the trade routes. And as you can see here on the right, this is a pretty intricate, complicated map that was fully navigated with the stars. There were no road marks. Back in the day, there was no compass. There was no tool. It was just people on camelback going from point A to point B, effectively being guided by the stars. And that's what, and pretty much the main trade routes, they used to have what was called the summer journey and the winter journey. So in the summertime, they would actually travel north, doing goods exchanges with the Persian Empire, with the Roman Empire, and then in the winter, when it's cold up north, they actually go south and go to Yemen and Abyssinia and trade with those regions, effectively facilitating the exchange of goods. Now, if we were to actually zoom out from this map over here, you come to recognize that this was connected with the Silk Route that extended all the way to China. Now, they exchanged a lot of goods and facilitated the transfer of goods, but the Arabs that lived in the central region maintained their isolation from a cultural, from a linguistic background for hundreds of years. And they didn't actually break that isolation and interact with the rest of the world and learn from it and contribute to it until actually Islam came in the 600s AD. But pretty much, you had the north journey, you had the south journey in the summer and winter, respectively, and the knowledge of the stars is what guided those journeys, and that's what got the Arabs to develop something that's called Anwa. And Anwa was effectively, you can call it the equivalent of ancient constellations. Some were primitive, some were elaborate. And examples of Anwa is, for example, the Pleiades. Was one that was well known. You're guided by the Pleiades at a certain point. So just like constellations of ancient, Anwa functioned as a way for people to navigate, as a way for them. This was their calendar. That was the way they kept time. People didn't know very well, year after year, how are things moving, month after month. Yeah, there were the lunar cycles, there were all these things, but to know that a year actually went around and, the turning of the seasons, that was their way. It was their stars. It was their way to identify that with the stars. And then also, those stars served a religious purpose for them, as some of those ended up being worshipped. And an interesting example of Anwa there is, that everybody knows the Pleiades, right? And which in Arabic called Athuraya. And you have Dibran, which that's the Arabic name for it. And, in the Greek mythology, Athuraya, you got the sisters and they're running away from Orion. But over here, it's a slightly different story, where Athuraya is actually one individual. And that individual is in love with a Debron. And a Debron is chasing his love in the sky for eternity. And by the way, this is pretty much the word Debron effectively means the follower of the Pleiades. That's where the name of the star comes from. And to the ancient Arabs, Athuraya was a very important was a very important group of stars because it signaled to them, hey, winter is about to start. This is the start of winter. Sounds good? So this is an example of what the ancient Arab constellations were. Now, another one is, for example, the star of Sirius, which was called Ashara. And Ashara, for some of the Arabs, they actually worshipped it as a god. And this one here, there is actually some ancient history that actually this might be related to Osiris, the ancient Egyptian god, and that somehow through trade, they ended up adopting that. Now, there are different sources, and a lot of them are in conflict, and you need to recognize here, all of those were oral traditions for hundreds of years. So in oral traditions, you have a lot of things that are lost. There's a lot lost in interpretation from, individual number one, passing it to individual 2 through 3, etc., over hundreds of years. But at the end of the day, at the time of coming of Islam, Ashara, or Sirius in this case, was being worshipped as a god in the sky, right? And then you have Canopus, another star that, or in Arabic, Suhail. That one actually people took it for a good omen, because you have the summer days, you have the dusty windstorms in the midst of the summer, and Canopus shows up around, later in the summer, and it indicates that, hey, the cooler summer days are coming. So people used to take that as a good omen, in addition to Sirius. So for people to see Sirius and Canopus, that meant good days were coming. So that's pretty much what those, to people, those were, and some of our literally individual stars, some of our collections of stars, like the Pleiades and Aldebaran. So pretty much when you look at digging deeper into the ancient Arab astrology, the gods that they worshipped pre-Islam, they were pagan, and they had their gods. In Mecca they had all the gods, but they all, all the statues of all the gods, but also every tribe had its own god. And just like the Greeks relating the gods to celestial objects, you pretty much had the ancient Arabs do the same thing. And this is, for example, a picture of Hubal, which was considered the most important god for the ancient Arabs. And Hubal was, a representation or a manifestation of the sun. Back in the day, again, this is a remnant statue, but back in the day, such statue, they would actually give it golden arms, like the sun's shining rays. This is pretty bright. And by the way, Quraysh, which was the main tribe in Mecca before Islam, that was their main god. And they perceived that he is the god of divination. He's the one who created everything. He's the one who actually guides their trade routes. And he's the one who brings rain in the winter season, which was an important source for them. If you live in the desert, the rain season is what replenishes the water in the wells and gets you to survive another year. So he was that god for them. And the manifestation of that in the world was the sun. Now we shift gears into his wife, Manat. And Manat in this case was the goddess of fortune. She kept track of time. She determined fates. And she was, Hubal's wife. And effectively, when you have the sun, you got the moon. Manat was the moon. Now, in this picture, actually, there are two other gods. So she's outflanked, on the right by, Al-Uzza, which was in this case, Venus in the morning star. People, the ancient Arabs didn't know that Venus, whether it shows up in the morning or in the evening, is the same planet. They called it the morning star and the evening star, and they associated a god with each one of those. So you have, one as the morning star and the other one as the evening star, and that's, Al-Uzza and Al-Lat. And Al-Uzza was effectively the god of honor, pride, and protection. And then you have Al-Lat, who is the goddess of war and peace, combat, and prosperity. And they were, Manat, Al-Lat, and Al-Uzza. Three of them were three sisters. Now, an interesting thing is, if some of you have read into Roman history, and about the story of Zenobia and the fight of the Palmyreans against the Romans and so on. The Palmyreans were Arabs, and they worshiped the pagan Arab gods. And pretty much the main character in the story, Zenobia's son, who was declared king, and she was the queen consort, his name was, and I'm going to butcher this because it's in Latin, it's Vabalathus. But what, as always in Latin, the V is a W. What it actually means is Elet, Vabalathus. And what that means is the gift of Elet. So you even have kings and others being named after those gods, and historical characters being named after those gods. And then you have another god here that was worshipped. His name is Dushara, and Dushara was manifested as Mercury and Jupiter at times. And for the Arabs who came in contact with the Romans, they related him to Zeus, and he was pretty much the god of justice, and he was the son of Elet. So just like Greek mythology or Roman mythology, you have characters related to the planets and the sun and the moon, and they're all interrelated, and you have myths and stories around each one of them.
Hey, Ahmed.
Go ahead, sir.
So Ron Schmidt asked the question, did this ancient Arabic astronomy grow from Zoroastrianism?
It's totally independent. There are some influences of Zoroastrianism. So the interesting thing is, when you look at the northern Arab tribes that interacted directly with the Persians and the Romans, they've mixed certain factors of Zoroastrianism or a pagan Roman religion into their mythology. But for the Central Arabs who are isolated, they sort of like developed their own unique aspects. And now here's the thing, for some of them, like Hubal, for example, it might have some ancient Greek origins. It might. And then, but that's also contested. Now, on the other hand, when you look at the three statues in the middle, since they were worshipped, the three goddesses in the middle, they were worshipped from, present day Syria and Iraq. So you can say from the southern Turkish border all the way south to the Indian Ocean. There are different manifestations, and in the south, you see him more presented more like African gods, but in the north, you see him looking more like Persian/Greek gods in the statues. But their origins are independent of both cultures.
Ron follows up with another question. Did the Central Arabs have a zodiac?
They did. So effectively, the Anwa, that was their zodiac. So it was the Pleiades and Sirius and Canopus and those stars. That was their zodiac before Islam. Plus, they've adopted certain things from, that were common to other cultures, like Orion. I think every culture has Orion somewhere, somehow, with its own unique story. Mm-hmm. But again, the issue with that era is that a lot of the things were oral traditions, and a lot of it was lost, from one generation to the next. Now, the Muslims, when they, after they expanded and started actually recording all these things, they try to record as much as possible of it and from different sources. But again, there's only so much you can record, right? Or you're going to retain after hundreds of years.
Because you had told me offline that prior to Islam, this was all oral. It was only when Islam really started that he started writing things down.
Yes. Yeah. Islam was a transforming moment for the Arabs, and we'll talk about that. But you're talking about a group of people who actually didn't write, and and upon the coming of Islam, it was estimated that Mecca had like 4 people who can read and write. You're talking about a city of like 5,000 plus people. Only 4 people can read and write in some estimates. Most people didn't know how to read and write, but they had a pretty rich, vibrant society when it came to poetry and oral traditions, which is how humans actually started developing and passing on information, in earlier ages. And then eventually humans got to writing, and they learned that with writing, you can actually preserve and record things longer. But for the Arabs, they actually never made that switch between oral to a written tradition until Islam.
Right. Well, let me just ask, does everybody have any questions on what Ahmed has
go ahead.
So
yeah.
Any questions out there? I don't see anything in the chat. Give them 5 seconds.
Hey, Ahmed, how many total constellations did they have at that time?
I tried to find a count. I couldn't find. I couldn't actually get an accurate count.
Okay.
Because
Thank you.
some go back and say, well, they had the 48 constellations of Ptolemy, and I'm like, they weren't even aware of Ptolemy. That doesn't make any sense. You have a lot of conflicting sources. I couldn't get to an actual count.
All right. Thank you.
So,
Any other questions for right now?
so the interesting thing is everything. Thank you, Suresh. The interesting thing is Arabs pre-Islam, everything was oral traditions. They just observed things and taught a generation to the next orally. There was no actual physics or theorizing what are those things. It was mainly astrology without much true astronomy. Fair enough. And the stars also to them, the stars in the skies was a sort of astrological superstition. And an example of that is that they used to look at eclipses, solar or lunar, or even comets passing by as this is a sign from the gods, and they can interpret it as a good sign or a bad sign in context of what's happening. And an interesting story is that, at the time, this is when Prophet Muhammad came, and his son passed away, and that was on January 27th of 632. We know that because we can calculate when did an eclipse occur in that year. But his son passed away. And then a lot of people started saying, well, and that day there was a solar eclipse. And when that solar eclipse happened, the same day his son passed away and they were burying him, you had some people, including Muslims, saying, oh, the skies are sad because the prophet's son died, right? And that was their interpretation, the superstition from back in the day. And then Prophet Muhammad ended up actually gathering the people and telling them, and this is in the recorded books, that, the sun and the moon do not eclipse for the death or the life, meaning the birth of someone. And then there are other written traditions from Prophet Muhammad or in the Quran saying that, don't, pretty much rejecting astrology and don't tie any of that stuff to your religion, that you need to go, there is no shortage of passages in the Quran saying, you need to go look at the skies, look at yourselves, look at the environment around you and observe it and learn from it and attempt to understand it, that it all comes from the wisdom of God. And this actually was a transformative moment for them because this actually changed their paradigm from a society that doesn't read or write, doesn't develop any science. They just relied on goods exchanges from the north to the south and stayed isolated from the rest of the world. This was a paradigm shift. So any questions so far?
Yeah, there are 2 more questions that are put in the chat. Carl Magnus asked, were there sacrifices? And I assume he means human sacrifices.
There were no records of human sacrifices, but animal sacrifices were always a fair game. All these gods, there were always animal sacrifices in front of them. And the funny part is, it's recorded in the books later that, the mice who would come and eat, they would sacrifice an animal, leave it in front of an idol, and then the mice will come and eat that animal, and they would consider that when the mice ate it, that effectively the god sent his servants to accept the sacrificed animal.
And then Angelina asks, did a zodiac tell stories about the figures they saw in their stars?
I'm sorry, can you say that again?
Sure. So I guess in the Arabic zodiac, were they telling stories about the figures that they saw in the stars, like the constellations? They have stories.
Pretty much, yeah. And that's what I cover. The example I gave, if I just go back a couple slides back, pretty much the example here of a Thuraya and a Debran, 2 in love, that they saw a Thuraya as an individual and a Debran as her lover chasing her in the sky. So you have some oral traditions like those that actually made it to us. And you have others that we only know the names and they were lost. So Canopus, for example, we know they took it for a good omen, but there is no other story behind it than it is for a good omen. Sirius, on the other hand, it was taken as a god that is worshipped and it's a good omen, but that is something that pretty much when you look at all the records, it was like it went from one generation to the next, and the reason why they decided to do that or what the origin story of it is unknown. On the other hand, you also have them identifying Orion as a hunter in the sky. But that sounds like every other civilization. Even if you go to cave paintings 40,000 years ago, you know, you can find Orion, and he was always a hunter.
Mm-hmm. Are there any other questions for Ahmed right now? It's all yours, Ahmed.
Sounds good. So pretty much, we talked about the Arabs before Islam, and how isolated they were, and how, you know, it was mainly astrology. There was no astronomy, not much astronomy there. Yeah, they used it for navigation, but it was mainly astrology. And it wasn't until, you know, upon the coming of Islam, and within the first, you know, less than 100 years, the Muslims pretty much conquered a significant portion of the known world, the entire Persian Empire, more than half of the Roman Empire, you know, with important regions like, you know, the Near East and Syria, and decent portions of present-day Turkey and Egypt and North Africa, all the way to Spain. And effectively that, you know, that whole conquest, you know, for, you know, the first time in hundreds of years, effectively, probably, actually, since Alexander the Great, you haven't actually had an empire stretching all the way from Central Asia. Even Alexander didn't get that because he didn't go west, but pretty much you didn't have an empire that's going from Central Asia all the way to the Atlantic. And, you know, the Arabs at this point, and, you know, led by the Muslims, they created a melting pot for cultures, for people from a Persian background, from Turkic background, people, you know, from African background, from, you know, Berber/Amazigh and Northern Africa background, you know, Europeans, you know, Goths from Spain. This was effectively a melting pot that brought a myriad of cultures and connected them all together. And we'll talk about the scientific output of some of those. But this ended up providing a revival of science in general, but specifically astronomy. And that revival started with translation of ancient texts, and then eventually evolved into critiquing those ancient texts, and then eventually developing new theories after critiquing the old ancient texts. Now, in this entire empire, Arabic was the language of science and astronomy for a millennia. And you'll find that a lot of books, including the infamous Almagest and Euclid's Elements book, they were translated from Greek to Arabic before they actually eventually got translated from Arabic to Latin. And you have certain names being corrupted as they went from Greek to Arabic, and then corrupted again as they go from Arabic to Latin, incorporating certain aspects of the Arabic language, like the AL before a name, including the name of the Almagest itself. It got Al from Arabic. So you have, you know, significant expansion, all these melting cultures, and then you have, you know, different ruling families, but it was pretty much a contiguous empire ruled by central government, initially in Medina, then in Damascus, and then in Baghdad. And at the time of the Abbasids, when, you know, it moved to Baghdad, you know, around 100 years from the start of Islam, slightly over that, about 120 years, the Abbasids formed what was called Bayt al-Hikmah, means the house of wisdom. And it was built in Baghdad. It was a huge building with the intention of, this is a center for science. This is a center for translations. This is a center for, you know, scientists to come, students to learn, for theories to be debated, for discussions around science to be discussed. And pretty much it was built around between 754 and 775. It was built by Harun al-Rashid, the infamous caliph from that era, and who was a contemporary at the same time. He had Charlemagne in France, and pretty much he built that and brought hundreds of scientists into it. And astronomy was one of the most important things that they discussed over there. And they started initially by gathering thousands of manuscripts in Greek and Chinese, Syriac, Aramaic, Persian, and then they, you know, Sanskrit from India, and they worked on translating those texts into Arabic. Now, Beit al-Hikmah itself, or the House of Wisdom itself, survived for another 500 years, but unfortunately, in 1258 AD, with the Mongol invasion, Hulagu Khan, the son of Genghis Khan, as he destroyed Baghdad, Beit al-Hikmah itself, actually, there is a very sad story about how they actually they executed the scientists, they, gathered the books, and they dumped them in the Tigris River for the Mongol army to cross to the other side. It was enough, there were enough books, and the Tigris River is a big is a big river. There were enough books and dead bodies that they piled in that big massacre and into the river that the horses managed to cross the river. It shallowed the river enough that the horses crossed from, the eastern side to the western side of the Tigris River. Now, a lot of books were lost, definitely in that period. But the good thing that also, one of the important things that the House of Wisdom did was printing books and distributing it across the entire empire. And this is how you find, and we'll talk about that slightly later, you find a book published in this region, and then 5 years later, it's being critiqued by another, astronomer, effectively on the other side of the continent, thousands of miles away. So one of the scientists who actually worked at Beit Hikmah, and I'll touch on him here, is Ahmed ibn Muhammad al-Farghani, and he is known as Alfraganus in the Western culture. During the Renaissance, that was the altering of his name. And by the way, there is a crater on the moon named after him. But he had a lot of contributions to astronomy. He lived between 800 and 870 AD in Egypt. He's originally from Central Asia, but his parents migrated to Egypt. And he wrote a book about the elements of astronomy and celestial motions, and it was effectively a follow-up of the Almagest, of Ptolemy's Almagest, and critique of that. Now, in his book, he focused on correcting the circumference of the Earth, the axial tilt, how to measure in the actual estimations the perihelion and aphelion of the sun and the moon. And he actually devised a very smart way when he came to the circumference of the Earth measurement. And that story starts with, the Caliph al-Ma'mun, who was the son of Harun Rashid. He actually gave him the test of go measure the circumference of the Earth. So what he did is that between two famous cities, Palmyra, present-day Tadmur, and Raqqa, both of them, between Syria and Iraq, the land is effectively flat, and they're not too far away. So what he decided to do was, effectively, both of those cities, based on the star measurements, we know that they're 1 degree latitude apart from each other. So using a leather rope, they actually went and literally measured the distance between those two cities. And that's how they measured, hey, we know that with 1 degree of latitude, the distance and the curvature is that much. Now, the interesting thing, and this is actually, when you look at what he ended up estimating, he estimated that for 1 degree of latitude, you get about 56 2/3 of an Arabic mile, not a European or modern mile. They had different, they had different scales for, before the standardizations of units, they had different scales. Now, converted to modern terms, that actually ends up being 40,248 kilometers for the entire circumference of the Earth when you calculate what he ended up coming to. Now, the interesting thing is, if you were to compare that to reality, we know the circumference of the Earth nowadays is 40,068. So that's a pretty accurate measurement, and it's mind-blowing because he's about 180 kilometers off. Now, remember, this is 1,200 years ago, and he got a really, good way of how to measure the circumference of the Earth. using, you can't measure the entire planet and over long distances, but over a controlled distance for 1 degree of latitude, you can measure that, and then using trigonometry, you can figure it out. Now, the interesting thing from the outcome of his work is, a couple 100 years later, 200 years later, in 1037, al-Bayruni, Abu Rayhan al-Bayruni, who was by himself. I could have a presentation that goes on for hours about him, and I'll say why in a little bit. But Abu Rayhan al-Bayruni, he figured out, hey, from Western Europe to East Asia, we're only occupying about 2/5 of the Earth's circumference. So in his book, he puts a theory saying, hey, there might be another continent on the other side of the planet, because they're 3/5 of the Earth's circumference. We're not aware of it, which is actually, so we're not aware of more than what we're aware of. So he was proposing that there might be a continent on the other side. And if there's a continent on the other side, there might be life, there might be humans, there is existence on the other side of the planet, which is, you come to think about it in 1037 AD, this is mind-blowing, right? And al-Bayruni himself, he's a very smart guy. If you start to think about, people in the past, they had the calendar before, and they had the calendar, broken down into months, days, weeks, and then hours for a day. But he was the one who actually went and he divided the hour into 60 minutes and the minute into 60 seconds, and ended up defining the hour and the minute in thirds and fourths. He was the one who ended up defining what the second is. And that was around 1000 AD. And by the way, there's also a lunar crater named after him. Now, the interesting thing is that the works of Alfraganus and al-Bayruni is what Christopher Columbus used to go and justify to Queen Isabella of Spain in 1492 to go and fund his expedition by saying, there is something back there. We can go to the Indies, to the Indies from the west instead of going through the east, and there is something over there. And he used those writings to tell her, hey, your investment is not going to be a losing one. We're not going to go and sink. There is something on the other side. So it is interesting, the influence in the impact of those writings on later times. Any questions so far?
I don't see anything in the chat. Does anybody have any questions? Nothing right now, Ahmed. All yours.
Okay, I'll keep plugging away. So I'll shift gears here to the translation of the Almagest. As everybody knows, it was written by Claudius Ptolemaeus, or Claudius Ptolemy, in between 147 and 150 AD, and its original name is Mathematicae Syntaxis, and pretty much it wasn't named Almagest. Now, the interesting thing about the name Almagest is that it's a combination of a Latin/Greek word that means majestic, and then al from Arabic. And as it got translated in the name of it, it effectively meant, you're saying al majestic, meaning the majestic book. And when it made it into Arabic, and then eventually when it got translated from Arabic to Latin later, the original name was forgotten, and the Arabic name Al-Majesti was the one that made it back to Latin and became the Almagest. So it's interesting how the name actually moved from one language to the next. Now, Almagest was interesting because it had a mix of a lot of things. It had astronomy. It has astronomical tables with longitude, latitude, and magnitude of the objects, and it also had constellations. But it also had a fair amount of astrology. Most of the astrology stories of the sky around the ancient Greeks and the Romans, and the early Romans of the time actually come from Almagest, from Ptolemy's work. Now, the Arabs attempted to translate it a couple of times. The first one, in 700 AD, That was the first translation. The second one in 800 AD, both translations were lost and didn't actually propagate until you have around 829 AD, the third translation by Al-Hajjaj ibn Yusuf ibn Matar. He actually was the one who made the current translation that ended up propagating for the future of history after that, and eventually being translated into, Latin from Arabic after that. So he was the one who took the Greek version, translated it to Arabic, and that translation stuck around. Now, an interesting thing he did was, given Islam's attitude towards astrology, he didn't discard the astrology side, but in his translation, he separated the works of Ptolemy into, here's astronomical information and here's astrological information. And you effectively have somebody attempting to separate, here is observational data and theory work and all that stuff, and here are myths and stories and all that stuff, separating astronomy from astrology. Now, who was the first one to separate astronomy from astrology? That's always a question up for debate, but it's manifested over here. There are others throughout history who have attempted to do it. Another interesting thing about Hajjaj is that he was also the one who preserved Euclid's Book of the Elements by translating it to Arabic, and then later that book got translated into Latin again during the Renaissance.
Hey, Ahmed.
Yeah.
Quick question. Can you discuss who the Ptolemies were and why they were so important?
Oh, sure. Yeah. You mean the empire, right? Or Claudius Ptolemy?
The start of the Ptolemies and why they were so important between the Greeks.
Okay, so to understand the start of the Ptolemies, you got to go back to Alexander the Great. Alexander the Great pretty much built an empire that stretched from ancient Greece and Macedonia all the way to Eastern Persia and parts of India today, encompassing in it the cradle of civilization in the present-day Middle East and Egypt. Now, after his death, you have his generals agreeing that he didn't have an heir. His generals agreed on, hey, we're going to actually split his empire. So there was one that captured Anatolia in Greece and Macedonia. There was one that ended up being, the predecessor of the Persian Empire. And then you have one in Egypt. And effectively, they broke down what they deemed as the important regions. And the one in Egypt, it had its capital in Alexandria. And the first of those, who was one of Alexander's generals, was Ptolemy I, hence the name, the Ptolemaic Empire. And they continued until Cleopatra and her defeat against, it was Augustus, and I think it was the Battle of Actium, and don't quote me on this, I'm going to butcher. I think it was 88 AD when it happened. I think it's 88 AD.
Yeah, that sounds right.
Is that right or wrong?
I think that's pretty close. It was the Battle of Actium, the sea battle.
Yeah, the sea battle, and then she committed suicide.
Right.
Sorry, I'm just looking it up here quickly. I'm wrong.
It was
31 BC. I'm wrong.
But it was the Ptolemies that linked the Greeks and the Egyptians, right?
Pretty much, yeah. That you're absolutely right. When the Ptolemies ruled over Egypt, that was right after the ancient Egyptians have collapsed. The ancient Egyptians had a rich astronomical knowledge. Astronomy for them was very important because they used it for construction, used it also for navigation like everybody, and also served religious purposes. And Claudius Ptolemaeus, he lived in Alexandria, which was the capital of the Ptolemaic Empire. And the Ptolemies, they built the Library of Alexandria, which later was destroyed by the Romans, and the whole story of Hypatia. But the Library of Alexandria housed all the knowledge that they could gather from Egypt, combining it with the knowledge of the Greeks, combining it with knowledge from across the world. And Claudius Ptolemy, he lived, during the Romans' times of ruling Egypt, but he had access to the Library of Alexandria and a lot of sources, and that's what allowed him to actually put together his book, Almagest. And this is why it became a very important book in astronomy in general. Does that answer the question, Suresh?
Yes, absolutely. And Yara just asked a follow-up to that. Was this book available in the Sham area when it was written? I mean, the Nabatean and the Romans in northern Jordan, could they have had access to it in 147 to 150 AD?
So the first translate that book was available. The first translation that was lost, and we have some records of it, actually came from a Syriac version of the book, not a Greek version of the book. So did it exist in that region? Given the language that it was translated into, that means it did exist in that region, that it was written in Syriac.
And the Nabateans were in Jordan, right?
Nabateans, they were in Jordan and eastern Syria, across the Syrian desert.
Carl Magnus asked, do astronomers today consider the translations division of mythology and empirical observations as the beginning of astronomical science?
Here's the thing, when did the science of astronomy start? I think it started with, the early humans who looked at the stars and started noticing patterns. I think that's when, and when you start to figure out patterns, that's the beginning of science. Now, of course, with everything, when you don't understand everything, you start to associate theories, and sometimes those theories are mythology, which is what happened. And for a time, especially, like during the Greek period, there was a lot of mixing, and you can see it actually during the Islamic astronomy. They actually separated the two from each other. And you see them actually doing that to other sciences. Like before chemistry, there was alchemy, right? Which was also a mix of mythical stuff and, what was perceived at the time as like, kinds of magic and all that stuff with chemistry. They separated the science from the non-science into alchemy and chemistry. So when can you call something the birth of a specific science? It's really hard.
Is alchemy another Arabic word?
Alchemy, yes. It's a combination. Yeah, it is a combination of an Arabic and an ancient Greek word. Yes.
Interesting. Great. I don't see any other questions, so go ahead.
Sounds good. So the interesting thing to Almagest is that, and we'll come back to, the Almagest had tables of star positions. It had drawings of constellations, and I'll first touch on what happened to those drawings of constellations. And it had the mythology side, which was translated but never actually expanded upon. But the drawings of the constellations and the star positions and the theory stuff, that's what the Islamic civilization contributed to and added to. And you can actually start to see what happened to the constellations. And this is actually from a book of the Fixed Stars by Abdurrahman as-Sufi, who lived between 903 and 986. He wrote this book in 968, and he started with what Ptolemy had for constellations, and he started detailing it more, adding more stars that Ptolemy didn't have. He corrected some star positions, and also he started assigning names to the stars, because if you're going to study something, one of the first things you need to do to it is give it a name. How can you tell the difference between star A and star B? And this is actually, I managed to find that in the Met Museum in New York, they have a copy of the book that is from about 1200 AD. So it's not the original book written by Abdurrahman as-Sufi or a copy from his era, but from about 200 years after. And it was mind-blowing. They have it all scanned, and they've shared the pictures, and I'm bringing some of those here. But the other thing is that in his book, you have the earliest recorded record of the Andromeda Galaxy, and he called it the small cloud. In his book, he calls the Milky Way the large cloud, and then the small cloud. And he debates, okay, what is that cloud? Right? Back in the day, they didn't know the whole concept of a galaxy. But to them, it was something that was, all the other clouds, we see them, the wind is blowing them as they move from point A to point B. But those clouds in the sky, actually, they don't move. If anything, they move with the stars. And that was another thing. The other thing is that there's a record of the Large Magellanic Cloud. And interesting thing is that all these galaxies in his book, where they were being called clouds of stars. And the other thing is that if you look at the book, and this is what's shown in the picture, the depictions in the book try to depict every constellation from two perspectives. One, where you're actually looking from the inside, looking at the sky. And the other one is if you are outside of a celestial sphere looking in, what would that look like? And this is what you can see here on the side over here. The upper image is Ursa Minor, as you would see it if you are looking from the outside of the celestial sphere. The bottom one is if you're looking at Ursa Minor, if you're looking from the inside here, from Earth, the inside of the celestial sphere. And you will see that with every drawing that he made. Now, here's the thing. They knew that stars were far away. There are theories about trying to quantify, okay, they knew that the star patterns were probably 3D, not a 2D image on a globe or a sphere. They recognized that, but they didn't know how to record that. So that was his approach. And that is one of the things that are debated in his books. And he doesn't have a solution to, which is, yeah, we can tell distance between stars from our perspective, but but that's effectively still a 2D perspective. What's the third dimension? They couldn't quantify that. So as you go through his book, and I had a blast actually looking through the book and reading a lot of the things that he was talking about. It was mind-blowing. I was like, I can literally stop everything and just do a 2-hour presentation about this book.
Because Al-Sufi is one of the most important astronomers of this era, right? Because
yes,
he was essentially Tycho Brahe 600 years before Tycho Brahe. In terms of recording the star positions and things like this. Actually,
I will talk about someone who was, Tycho Brahe before Tycho Brahe was Tycho Brahe. But a Sufi was more, he actually didn't do much observations. His book was more of translation and recording things and more on the theory side. He was more of a theoretical astronomer.
Okay.
Fair enough. Observational / theoretical. You have others who are experimental, taking actual measurements and all that stuff. And, we go back to the House of Wisdom. The House of Wisdom facilitated these books being written somewhere and then being printed and debated, in another region. And if it wasn't for the House of Wisdom actually effectively not only acting as a teaching and a research institute, but actually it acted as a place to rewrite, back in the day, books were rewritten by hand. And it acted as a place where books were rewritten, duplicated, and transferred from one region to the other and propagated across, the Islamic, empire at the time. So here's another one, and who can figure out this one, right? That's an easy one, right?
Yep.
It's Orion, right? You can see the shoulder, you can see the stars, the sword, the leg, etc. And he went, and as you can see, the picture on the right, the drawing on the right is if you're looking from outside the celestial sphere, and the one on the left, if you're looking from Earth onto the sky. And in his approach towards naming objects, he took a pretty interesting approach. And I was chatting with some of the people before the meeting. As he started naming stars, he started, he didn't come up with any like very tough things that we couldn't relate to. He took things that actually related to the objects as we saw them or perceived them as humans. So, for example, everybody knows that the leg of Orion is called Rigel, right? That comes from the Arabic word rijl, which means the leg, right? So what's you effectively, if you know that star name and you know that it's the leg of Orion, you know the word for leg in Arabic. The same thing for the sword of Orion, right? What's the name for it? It's Saif. The main star in the sword of Orion, that's the name for sword. Or Al-Nitaq, the belt of Orion, that's the word for belt. Or, Betelgeuse, which that got corrupted many times. But the original word, Baytul Ajuz, the shoulder of Orion, that effectively means the shoulder of an individual. And you see that not just in Orion, but you see that across all of the constellations. The main star in Draco, what is Draco? Draco is a snake. And the main star Thuban, that is the word, Thuban, which is snake in Arabic. So that was his approach to naming things, is we see that, okay, this is a belt, I'm going to use the word for a belt, right? This is a sword, I'm going to use the word for a sword. This is a leg, I'm going to use the word for a leg. Like for Leo, for example, the main star is Asad, which is lion, right? Or in Lepus, the rabbit, the main star is Arnab, which is rabbit in Arabic, right? So if you know all these star names and what feature in that constellation you're talking about, you pretty much know the Arabic word for that. And he put a lot of effort into cataloging and naming these stars, because that's what people needed after that. As those stars are identified, now they could be studied. But before you identify and give it a name, it couldn't be studied. All the previous efforts, by the Greeks and the others, okay, there's too much. The way they looked at it is like, there's too much in the sky. Let's try to group it into constellations. And constellations were effectively groupings of stars, identifying a couple bright ones and maybe giving them names, distinct ones. But then for the rest of it, it's like, okay, here's just a grouping of the stars, and that's it. So yes, you'll find the names Sirius and Canopus and in Taurus, in different constellations. Like, yes, you'll find Greek names and sometimes Roman names, but then the rest of the constellation stars are not named. It wasn't until the Arabs, or specifically Sufi, came out. Ahmed Sufi came, and he started actually naming all these different objects and assigning names to them. Now, this is, Ursa Major, same exact pattern of identifying stars, naming them, same exact approach of seeing it from inside the celestial sphere, from Earth, versus seeing it from the outside of the celestial sphere. If you want to, after the meeting, I can send you the link to the book. There is hundreds upon hundreds upon hundreds of images that were scanned from the book, and it's just mind-blowing looking through it. And if you understand Arabic, and as I was reading everything, it was, for somebody looking at it, over 1,000 years later, it's just mind-blowing.
So Ahmed, I dropped a link to the Met Museum piece about this book on the chat. Ron Schmidt had asked, has the Arabic alphabet changed much since 8950? Would a modern Arabic speaker be able to read this book?
Oh yeah, it hasn't changed. It wasn't that hard for me to read. Yeah.
Yara says she wants to cry.
Why?
It's amazing.
Yeah. No, this book is mind-blowing, and I wish that it's one of the books that a lot of the theory and a lot of the things that are being discussed, I wish it gets translated and taught to people. Not that we haven't figured out the answers to a lot of things, but as a way to think about the thought process, thinking through problems and arriving at solutions. This is a mind-blowing book. And Yara, I assume is it safe to assume you're a native Arabic speaker?
Yes.
So you can read what I'm showing here, right? In Arabic.
Read, and I just want to buy it, and I want to touch it, and it has a beautiful handwriting.
Yeah. Yep. You can find, in that book, and in the Met Museum, they've done an amazing job of like scanning it and putting it out there. As I was looking for it, the different constellations in Ptolemy's book, and there's 48 constellations in the book, and then they have some of the pages that are talking through the theory work, and I started reading them, and it was also mind-blowing just what I was reading through, and I was like, I can drop everything and just do a slide, presentation, a slide deck around this book. That's how good it is.
Ahmed, do you know if this book's for sale anywhere?
So this is a copy, if I'm not mistaken, when I read from 1200. I don't know if this book is on sale. They have it in the museum, but I don't know if it's on sale anywhere.
And then Paul Gate asked, why were both the inside and outside perspective important to be shown?
The reason for that is, and this is not something I covered here, is that one of the things you find that they were doing is that as they were doing star maps, some of the star maps they were doing, they would have a brass sphere, and with a nail, they would actually mark up the star patterns. So you have the perspective looking from the outside versus the perspective looking from the inside. Because if you're making a brass sphere and marking up all the stars on it, you're not going to be on the inside of that sphere. You're going to be on the outside. So that was one of the ways of mapping the sky with a spherical map.
Very cool. Anybody have any other questions about this book or anything? All yours.
Thank you, Suresh. Okay, so this is one of the ways how constellations were preserved from Almagest, the drawings, and then expanding on the names. At the same time, you have somebody who came before us, Sufi, Muhammad ibn Musa al-Khwarizmi, and he played a very important role in science in general and in astronomy specifically. And he lived between 780 and 847 AD. He's born in Khwarizm, which is in present-day Uzbekistan. His parents, when he was a child, moved to Baghdad, which was the center of science, a city at the time of about 1 million people. And when he was there, he managed the House of Wisdom. He was one of the key managers of the House of Wisdom, and a critical one. And one of the most important things that he did is that he managed a large group of scientists, and his research was in astronomy, in geography, and mathematics. And just as an example, we have recorded the names of 70 people, 70 cartographers that worked for him. And we also have the recording of the names of over 100 astronomical observers that worked for him and did number crunching and analysis for him. So he was not just an individual, he was an institution. He wasn't just one person working on his own. He was one person who was directing the work from given work and work direction to a lot of people. Now, he's important for astronomy is because he wrote a book called Kitab al-Jabr, or the Book of Algebra. He's considered the father of algebra because in that book, he changed the approach. He defined, in algebra, the most important thing is X, right? The unknown you're trying to solve for, right? And he was the first one who started setting things up as equations. And he set up algebraic objects that we can solve for with rational, irrational numbers and geometric magnitudes in that book. And then he also solved linear equations and quadratic equations. That made him the father of algorithms. If anything, the word algorithm is actually a variation on his last name, al-Khwarizmi. Al-Khwarizmi, algorithms. That's where that word came from. And the word algebra came from the name of his book, Kitab al-Jabr, the Book of Al-Jabr, or Book of Algebra. So this was a big contribution that he did to math, but he also carried that contribution over to astronomy. So remember we talked about constellations, and in Ptolemy's book, there were the tables trying to capture star positions in latitude, longitude, and they had a lot of errors in how to quantify that. And al-Khwarizmi actually ended up writing a book called Zij Sind Hind. And you'll find the word Zij itself is actually meaning, it's an astronomical handbook with tables to calculate celestial positions. That's effectively what it means. And he wrote the first one, and then hundreds of these books ended up over the next millennia being generated and developed. And in his book, he contained movement tables for the sun, the moon, the planets, and all the main stars that are in Ptolemy's Almagest. Now, the other thing that he did was there was the ancient Indian astronomical tables called the Siddhanta, and he got somebody to translate those, and he reconciled them with Ptolemy's Almagest and brought them together into a big book. The reason why he adopted those is that while Almagest had a decent number of stars to start from, and by the way, he wrote his book before Sufi ended up naming all the stars So he used some designations for some, letter designations for some stars. But Almagest at the time was the most inclusive, or the largest encyclopedia of stars. So he started with that, but the measurement methodology in the Almagest was pretty limited and had a lot of flaws in the measurements. But the Indian astronomical tables were much better. So he brought those and reconciled them together. And he wrote that book, The Zij of Ascend Hind. Now, the other thing that he did in that book is that he went ahead and he set up the time in cyclical periods, that the positions of the stars in the sky are cyclical periods throughout the day, throughout the year, etc. And he focused on capturing the motion of the celestial objects as sine functions, as the objects rise in the sky and then they set. So effectively you have a sine function, and if you have the time as an input, you can actually solve for the position of the celestial object, and now you know where it is. Now, this was considered the first Zij book, and you'll find that after that, he actually set a pattern that was followed by so many people after that. And just to put things into perspective, when it comes to Zij books, there's over 200 of them that survive until today. And with each iteration, they expand more and more and more on the stars. This is just an example. And, 200 of them surviving over 1,000-year period, and assuming the 200 were the only ones written, there were probably more written, but they were lost. That effectively means that every 5 years you have a new evolved astronomical table being generated. And those were not small books. Now, where the House of Wisdom actually played a very good role is that with the printing and the distribution of the books of Al-Khwarizmi, as he was writing them, you'll find there was an astronomer who lived in Madrid, in Madrid, and later in Cordoba, in Muslim Spain at the time. Her name was Fatima al-Majritiyya, meaning the one from Madrid, and she was revising his calculations. She was enhancing his book within 5 years of him writing his book. That's how communication, across an entire empire. You have things being printed in Central Asia or in Baghdad and being critiqued on the other side of the world within a very limited period of time. For that time period, of course, without technology and internet and everything, this is mind-blowing. And this is actually what facilitated that. It became sort of like a science. How do we record star names? How do we record star positions? And how do we set them up as functions? And you pretty much have every person trying to come up with his own way and trying to actually outdo the other one in the accuracy of his measurement, in the accuracy of their measurement in predicting the star names. And pretty much in those books, this is where you see that the previous approach of taking things longitude, latitude for star positions being dropped, and then the altitude and the azimuth being adopted as the way. Even the word azimuth comes from the Arabic word asemt, which effectively means the angle from the north. That's what it means. And altitude, the altitude is from Latin for the angle from the horizon. So that one is actually of a Latin origin. But the azimuth was the unique word that got added there, and they would capture altitude, azimuth, and of course magnitude of that star. And you see that being adopted back then, and until today, we all still use altitude and azimuth for our observations, right? It's one of the easiest ways to find something in the sky. If you know your sky and you're oriented properly, and you know where north is, anybody should be able to find anything with altitude and azimuth, right? Any questions so far?
Yeah, Ahmed, Yara's asking, what is her name again? It's Fatima, right?
Her name is Fatima al-Majritiyya. And she was working with her husband, who was a chemist/astronomer, but she was purely an astronomer, and she was interested in the calculation side of things.
Does that answer your question, Yara?
Yes, thank you. Thank you.
Does anybody else have any questions for Ahmed? All yours.
So thank you, Suresh. And thank you, Yara, for the question. So you have these books being generated, and this is all more what you can call the theoretical, the theoretical and then the observational, and people are actually making measurements and recording them and getting better and better at them. Now, I've highlighted one here, in red, the Zij Sultani, and this was done by Ulugh Beg, who lived between 1393 and 1494. And Ulugh Beg is actually a very interesting character because he wasn't only an astronomer. Ulugh Beg was the son of the Sultan of the Timurid Empire at his time. And his dad, his name was Shah Rukh, he convinced his dad to build an observatory. We'll get to that here in the next slide. But he lived in Samarkand, in present-day Uzbekistan. And here you can see their empire actually, within the Muslim world stretched reasonable size. Now, interestingly enough, his great-great-grandfather was Tamerlane, who's famous in history, and which directly relates him to, about 200 years plus ago, his greatest grandfather was Genghis Khan of the Mongols. And it's interesting how the Mongols invaded, the Muslim empire, but then they themselves ended up actually adopting Islam. And then, they ended up adopting Islam and they became elite rulers and they contributed to the sciences. And by the way, the picture of him here is actually an ancient picture of him from a book that is about slightly after his time. But going back to Ulugh Beg, interestingly enough, he got to rule the Timurid Empire after his dad for a couple of years, not a short period of time. But his main contribution was in the field of science, not as a ruler. And he was very skilled in math and astronomy. And he wrote books. He worked with astrophysicists and astronomers at the time. And during his dad's reign, he convinced his dad that we need to build an observatory because he wanted to get better measurements of the star positions. So at the time of his dad, he got his dad to fund it, and he built a huge observatory. And I'll show you the concept of how it operates. But it started operations in 1420. And his first director was Ghayath ad-Din Jamshid al-Kashi, who was the first director and also the architect of the observatory. And then there was another astronomer who worked with them, Salah ad-Din Qadizad al-Rumi, who was also famous and got to serve as the second director. And then there's Mu'in ad-Din al-Kashi, who also got to serve as the third director of the observatory. And then there was Ali Qushayji, and Ali was actually interesting because later he gets to move to the Ottoman Empire, lives in Istanbul and Constantinople, and he was teaching astronomy and one of the leading astronomical figures in Ottoman astronomy out of Istanbul, for the rest of his life. So he's an interesting person to talk about, but unfortunately I won't cover him much here. But he was also one of the primary astronomers here that worked here. In addition to that, there were over 60 mathematicians and astronomers working in that observatory, observing star positions, recording them. Now, the whole concept of the observatory, before we get into the details, was based off of how a sextant operated. You have two mirrors with light being reflected off of them, and then you look at your object, you line it up, and that's your zero. And then you start actually rotating the arm of the sextant, because the upper mirror is only half a mirror to the object that you're looking at. The difference in the angle is effectively the altitude of the object from the horizon. You can also do that in the horizontal with a compass. And this way you can measure, the azimuth of something from the north, and then off of the horizon. It's pretty easy that way. Now, as everybody knows, with basic, angular displacement, at the center of a rotating object, the change of the angle, you can change something by 1 degree and it's not that noticeable. But then over a long distance, it gets to be very noticeable. And that was the big concept behind the observatory and the way they constructed it. It was effectively a humongous sextant. And that observatory here in a model now, part of it has been destroyed, but it's still a historical site in Uzbekistan that can be visited. And as you can see here, in this mock-up, you can see the sextant is on the top. And then you see from the inside, this is pretty much the base of the sextant, where they would actually be able to find the reference point within that sextant to measure the altitude. So, so pretty much these are actual pictures from what it looked like. And back in the day, those walls, now they're corroded. Now we're talking 600 years after. But back in the day, those were covered with marble and they had the degradations. And pretty much the arm of the sextant, which is effectively the magnification of your change-up angle, was about 50 meters stretching down this entire region. Now that's 164 feet arm. It was probably made out of wood, maybe connected with metal joints. Unfortunately, it didn't survive. The rest of the observatory luckily survived. But you can see this is big. So now they can actually see fractions. They can measure fractions of a degree difference between one object and the other. So Ulugh, with having this humongous instrumental tool, big humongous sextant, he pretty much wrote his own vision. He called it Sultani, meaning of the Sultan, the ruler. And it was, he was at the time when it was published, he was the ruler's son. And Zish Sultani was written in 1437 AD. And they could actually get a very accurate measurement of the sun altitude, of the stars and planet altitude, the altitudes, the duration of the year by the movement of the sun, and then the periods of the planets. With that big sextant, they were able to measure angular changes to 9 decimal places, and around between 87 and 90 degrees, which is almost between perpendicular and 87 degrees, they could even go to 11 degrees, something about the mechanism that they used. So this was pretty good and very accurate. It's mind-blowing, the tables that he generated now and how accurate they are. The interesting thing about Zish tables is that they didn't stop until today. NASA ended up actually adopting the same methodology in generating star tables, and they still update star tables regularly. Now we have much more sophisticated equipment, but it's rooted in all that tradition of generating those tables of star positions and continuously updating them and critiquing them. Now, in his measurements, this is the part that's mind-blowing. Ulugh ended up actually measuring the length of a tropical year. So he measured it at 365, 5 hours, 49 minutes, and 15 seconds. He was off by 25 seconds. That's how accurate he was. And just to put things in contrast, Nicholas Copernicus, who comes 88 years after Ulugh passed away, was able to measure the length of the tropical year, but his accuracy was 30 seconds. He was 30 seconds off. So that for its time, that was a very good calculation. The other thing that he calculated was the axial tilt of the Earth, and he calculated as 23.5047. Now, the interesting thing is that the actual tilt is 23.4392. So you can see he was very accurate. Again, given the tools that they had, the manual tools that they had. Now, Ulugh, as an astronomer, he had another major contribution to astronomy, where he ended up building the Ulugh Madrasa, effectively meaning school. And in that you can see actually, it's a historical site that you can visit today. And each one of those corners was dedicated to teaching a different scientific subject. They taught theology, but they also taught medicine, geography, astronomy. Ulugh himself taught astronomy and mathematics in the madrasa that he formed. The other interesting thing is that himself and the other astronomers, which all of them were before Copernicus's time, all of them in their writings, they were teaching and writing about heliocentricity. I try to dig into when did geocentricity shift to heliocentricity in Arab astronomy or Islamic astronomy. I couldn't get my finger on what the exact point was. You can see actually proposals going back to the late 700s, but it's not really yet. And then the Almagest being critiqued for heliocentricity, but it's not the common theory. It's not until much later, by the time of Ulugh Beg in his time, heliocentricity was the dominant theory of the setup of our solar system, and that all predates Copernicus and his heliocentric model.
Ahmed, just to be clear, because we have some beginners on this call, heliocentricity is the sun-centered solar system versus the geocentric is the Earth-centered, right?
Yes. Yeah.
Just to help.
Yeah. So yeah, with this, this model of an observatory, there were duplicates of it on a smaller scale in Baghdad. There was another one in Isfahan in Iran. There were other ones. There was one in Cordoba. Unfortunately, a lot of them got destroyed in different wars. The one in Baghdad got destroyed by the Mongols. The one in Cordoba got destroyed during the Spanish reconquest of Spain and the expulsion of the Muslims from that region. That they expelled the Muslims and the Jews from that region, and they destroyed certain things. One of them was the observatory in Cordoba was destroyed, but pretty much that was the model of course, the other ones were a smaller scale than this one, but effectively that observatory, Ulugh Beg Observatory, was the model for that kind of an observatory of that time, and that this madrasa model was the model that you will find all over the Muslim world for teaching sciences, where people would come over, and you have students, you have scientists sharing and researching stuff, and writing books and rewriting books and duplicating it. And you'll find that in Cairo, in Damascus, in Baghdad, in Samarkand in Central Asia, in Bukhara in Central Asia, in Isfahan in present-day Iran, in Cordoba, in Toledo in Spain, in Qayrouan, which is in present-day Tunis. You'll find it all over, the Islamic world at the time. That approach of an institution for teaching sciences, and astronomy was a key science that was taught. With that said, this is pretty much my talk. Now, any questions?
Yeah, any questions? Feel free to just ask your question verbally. You don't have to put it in the chat.
Yeah.
I know that Paul Gate had asked, can you give a little more information about the House of Wisdom? Just general information about it.
The House of Wisdom, the House of Wisdom was built during the time of Harun Rashid, and I shared the date of when it was built. The interesting thing about it is that the idea behind it was there was a lot of, the Muslims got the exposure to a lot of cultures, and then you have a big movement of translating all these texts. And the Caliph at the time was like, okay, I need a central location to bring all the scientists and consolidate the science and effectively create a melting pot for all these pieces of knowledge. And he built it. We have, the drawing I showed, that there were depictions of it from earlier, if I go back, this is actually a depiction, the picture on the right, the depiction from around that time of the House of Wisdom, where somebody would be sitting down teaching and there'd be students in front of them. You can see actually stacks of books in the background. And it was constructed, the picture on the left is more like, okay, this was the typical style of a madrasa, or the House of Wisdom was probably modeled the same way. And you can see that in Ulugh Beg's madrasa and in other madrasas, the way it's set up. And pretty much at the time, because the empire was very rich, the Caliph actually, Harun Rashid, and others before him, if you're a student of science, the government covered your expenses, they covered your shelter, and they even had hospitals to cover your healthcare and stuff like that. And there were, records of actually scientists who wrote a book or translated a book or, commented on a book, whatever scientific output that they developed. And back in the day, paper was heavy. It would go and they would put it on a scale, and that whatever that weight was, the scientist would get its equivalent in gold. So science was, greatly rewarded at the time, right? You give a scientific output, you'll get its weight in gold. And that was the standard that was set up. And that's what made the House of Wisdom a very important center of knowledge in Baghdad, but it also extended to the vast empire.
So Ahmed, I was reading about this. So the sack of Baghdad, and I think it was 1258.
Yeah, 1258. Right? Yeah, by the Mongols. Yeah,
1258. That was such a shock, losing the House of Wisdom and the other learning centers, that galvanized the other Muslim rulers against the Mongols, because they were afraid that they were going to go to Palestine and Egypt next and destroy those learning centers.
Exactly. Yeah. They were, because they were, the Mongols, they came out of Mongolia and pretty much invaded east towards China and then west towards the Muslim world. And unfortunately, they left a bloody trail, a lot of cities, and they were famous for their, pyramids of skulls of the heads of the executed populations. And they destroyed knowledge. They didn't read, they didn't write, and they destroyed knowledge along the way. A lot was lost. And the biggest tragedy of that era, which unfortunately not a lot of people in the West are aware of, in 1258 was when they sacked Baghdad. And in the records from that era, interestingly enough, by the Arabs, and some of it even by Mongolian historians who wrote after that, wrote about how this was a city of 1 million people, and how it was a big massacre of executing people, piling up the bodies, and how the House of Wisdom, specifically the books themselves, were dumped in the river, in addition to the dead bodies of the scientists, and they were used as a bridge to cross the river and invade the next land. It wasn't until the Mamluks of Egypt raised an army, and I forgot what year exactly, and defeated them in Ain Jalut in present day, Palestine.
And there was another Mongol leader, the ruler of the Golden Horde. I can't remember his name, but he had converted to Islam. And after the sack of Baghdad, he helped to fight off the Mongol.
Yeah, Genghis Khan. Yeah, the Mongols themselves, I think they were shamanist in their religion, and then you start to see certain tribes as they invaded West and got to, even if you're in the invader and killing people, you still start picking up part of the culture of the invaded society, and you start to see some of the tribes converting to Islam. Now, about 200 years after Genghis Khan, pretty much all of them were converted, and the lands that the Muslims lost to the Mongols were retained back.
Got it. So Ron Schmidt asked,
interestingly itself, the Mongols themselves, they joined the big melting pot that the Islamic civilization created. And Ulugh Beg, effectively, he is a Mongol. He is a descendant of those who came out and destroyed culture. And he himself was a creator of culture.
So Ron Schmidt asked, can you give us any details about the development of their astronomical tools like the Astrolabe?
There are so many astronomical tools, and Ron, that's a big can of worms. I can't answer it in a couple.
Maybe that's
minutes. That's another presentation, but it's pretty interesting. Like, I touched on it with the Ulugh Beg Observatory, and again, I showed things as, okay, the concept behind it is a sextant, right? They didn't have telescopes back then, right? Sextants have scopes, but the whole theory of you point one tube that you're looking through at the horizon. Now you can see the horizon. And they used to have metallic crosshairs. Sometimes they'd have a piece of glass with crosshairs written up, with crosshairs etched on it, but it wouldn't be actually an optical object. So they would do that. And then you would go and measure the distance between the horizon and then the object in the sky. And that's how you measure the altitude. That was a key way to measure the altitude in the sky. Now compasses and other things that, they already had some of those tools. And yeah, Ron, you're opening a can of worms.
So Ron and Angelina and everybody else, feel free to ask him directly. You don't have to put it in the chat now. So I'll read Angelina's question. So she noticed a theme of beautiful radial patterns in the Arab architecture. Is this meant to represent the cosmos?
Oh, you mean like on buildings and stuff?
That's what I think she meant. Yeah.
This is not necessarily meant to represent the cosmos. So the difference between Arab, I'll just show a building here, or actually my last slide would do.
The last slide had a beautiful one.
Yeah, the last slide, yeah. This is an interesting way of architecture, and the closer you look, you actually find that these are constructed out of mosaics of very small pieces that was called fusay. And the art behind it, Muslims didn't actually, given that Islam is a very monotheistic religion, depictions of idolatry and other items, were actually prohibited amongst Muslims. So Muslim artists shied away from drawing pictures or iconography on the walls or statues and stuff like that. But then they got really creative with that mosaic approach of decorating things and in geometric patterns. And it became an art style where they meshed different cultures. I don't know the exact history, if it actually something that they adopted from someone else or they developed it. I don't know that history.
Yeah, I've seen some of this in India and Egypt and Morocco. Some of this is stunning, just stunningly beautiful.
Yeah. And when you come to think about it, and this is all made out of small pieces and the decorations, and you can see, like the rosy pattern here on the side of the picture. It's just mind blowing what they used to do. And this probably took thousands of people to put together. But if it's indicative of anything, that just tells you how much they valued sciences, how they viewed a place where they actually, and by the way, mosques were built in the same pattern. So they looked at mosques, the place where we worship, and the place where we learn science and exchange information, as the most two valuable things. If you look at the Islamic Empire, you'll find that the most common remnants or historical sites are going to be either a mosque, or it's going to be a madrasa, which is a school. Now, you'll find in certain regions, bordering regions, you'll find castles and forts and the like, but you're not going to find castles. It's not like Europe you're not going to find palaces. It's not like Europe, during the Middle Ages, where there were lots of palaces left and right. No, there were actually a lot of investment into, religion and then God and defending the nation. That's where the government infrastructure went towards, in addition to other projects that they did, building dams and so on. But science to them was very important. And, interestingly enough, it's coming from the Arabs, who before Islam didn't read, didn't write, didn't actually contribute much to science. You can call them an illiterate group of people. That was a big change to go from this into the leaders of science for a millennia.
Yeah, and Ahmed, the other thing too is as they built these structures, they would import artisans and architects and scientists from all over.
Oh yeah,
not only the Muslim world, but also the European world. They would just import these people to do the job, right? From thousands of miles away.
Absolutely, yeah, absolutely. By the way, there was the empire itself had a lot of tolerance. Had a lot of religious tolerance, and there's the writings about how it was a Jewish golden age when the Muslims ruled Spain, and unfortunately, when the Europeans, or specifically because the people in Spain were also European, they were Visigothic, and a lot of them actually converted to Islam, and some of them were Jewish and they remained Jewish. And some were Christian and remain Christian. But when during Reconquista, when the Christians reconquered Spain, the first thing they did was they expelled the Jews, and then they expelled the Muslims, and there was a significant scientific loss for Spain in that period. But it was a pretty open culture of you know, you can come and you can contribute independent of your religion. And you see that in all fields.
Excellent. Does anybody
Anybody who
else
can
have any
come and contribute
questions
is
or
welcome.
comments? Anybody else have any questions, comments?
Was
I
Arabic
think, go ahead.
was Arabic astronomy always heliocentric?
So Arabic astronomy, before Islam, we do not know. It was probably geocentric, because if you look at any primitive, astronomy, initially they start with heliocentric. Effectively, you're looking from the inside out, and you're thinking you're the center of whatever you're looking at. And so all astronomy starts from, geocentricity at some point, right? But then you can start to see that Arab or Islamic astronomy, it's not fair to call it just Arab, because you have Persians, you have Turks, and you have people from the Indian subcontinent and others. Some of them became Muslim, some of them didn't become Muslim, but they all contributed to that. But it was all under that culture. You can actually start you can see the debate of geo versus heliocentricity going back to the late 700s, which is very early for Islamic astronomy. You can see that debate. And what I could tell is that by the 1300s, everybody was talking heliocentricity, not geocentricity. When did that shift happen, where it became the common theory that everybody adopted? That I couldn't figure out.
Are there any other questions, comments? Ahmed, this was fantastic. You did an amazing job.
Thank you, Suresh.
There's a lot of thank you notes in the comments for you.
Thank you.
Well, if there's no other comments.
I got one last comment
next,
after you're done, Suresh.
No, I was just going to say the next beginner special interest group session will actually be our first observing session, hopefully, of the year. It's scheduled for Saturday, April 29th at Metcalf Field, which is near Afton, at about 7 o'clock. Of course, that depends on whether or not the snow actually melts by then and the field dries out. So pay attention to the Minnesota Astronomical Society's website, mnastro.org, for updates on that. But again, it's April 29th, Saturday at 7 o'clock. I want to thank Ahmed and everybody for contributing to this presentation. I saw that we peaked at 38 people, which is a pretty good number for us, especially in the wintertime. Ahmed, do you have something else you want to say?
Yeah, I want to say thanks to everybody for this opportunity. I had a lot of fun researching this. And for the ones who know me, my first language is actually Arabic. And I grew up in the Middle East and came here later in my life. And I've always, appreciated the sky. I got a kick out of it. And I've always looked at the sky and knew that we, as Arabs and Muslims, we have a very deep history in astronomy. But I didn't actually dig into the details much until actually this time, digging into theory and what are the different things that happen. So thank you for giving me the opportunity. I had a lot of fun preparing for this. And my last thing is, I always have to put in a shameless plug for join us star parties at ELO. It's a lot of fun. Sorry, Suresh, for competing with your BSIG stuff.
No, it's all good. There's no competition. Ahmed, this won't be the last time. You'll be back. I'll grab you for something else.
Thank you, Suresh.
Well, anyway, thank you everybody for attending. Hope to see you again outside in April.